Now for Chapter 2, Solute Transport. We're now going to discuss reabsorption and secretion in some detail. Solute transport involves transport proteins that are embedded in the cell membrane of the nephron cells that mediate reabsorption and secretion of solutes, and we're also going to take a look at water transport. Acquired defects in these transport proteins are the cause of many kidney diseases, and also these transport proteins are important drug targets. Transport mechanisms. You have simple diffusion, which means that a solute moves down its electrochemical gradient, no energy is required. Then you have facilitated diffusion, which means that a molecule moves down its electrochemical gradient, but it does so attached to a membrane-bound protein. Again, no energy is required. Active transport is when a solute uses a protein-mediated transporter using the energy of ATP to move a molecule against its electrochemical gradient, again requiring a protein-mediated transporter. Uniport is when a transporter moves a single molecule, such as the take-up of glucose, into skeletal muscle or adipose tissue. This is an example of facilitated diffusion. It's one solute moving along the membrane on its own through a single transporter. Symport or cotransport is when a coupled protein transports two or more solutes in the same direction. Classic example here is sodium glucose transporter or sodium amino acid transporter. Antiport is when a coupled protein transports two or more solutes in the opposite direction. So saturation kinetics is a very important concept to understand. So let's say you have a membrane. Here's a membrane, and in the membrane you have these transport proteins. And these transport proteins are carriers that are used to transport molecules across the membrane. On one side of the membrane you have the molecules that are using these protein carriers. Now, as the concentration of the molecule on one side of the membrane increases, the rate of transport across the membrane increases. Now remember, everything in physiology is about a rate. When these protein carriers transport a molecule across the membrane, they do so at a rate. Rate is in milligrams per minute. That's the rate. So, as the concentration of the molecule on one side of the membrane increases, the rate of transport across the membrane will increase. At some point, these protein carriers become saturated. Once they become saturated, you continue to transport. It's not that you stop transporting, you continue to transport. But when these transporters become saturated, you transport at a constant rate. This constant rate of transporting is known as transport maximum. Transport maximum is a very important concept to understand right now. Transport maximum is a constant rate of transport. This is a constant rate that occurs because the transporters become saturated. And that's the concept of saturation kinetics. You can increase the transport maximum by increasing the number of functioning transporters. So transport maximum is directly proportional to the number of transporters. And that is transport maximum. Another concept about transporters is competition. Substances of similar chemical structure may compete for the same transporter. For example, glucose and galactose will compete for the same transport protein. Primary and secondary active transport. In primary active transport, ATP is hydrolyzed to directly move a substance against its electrochemical gradient. For example, the sodium-potassium ATPase or the calcium-dependent ATPase. In secondary active transport, ATP is hydrolyzed to indirectly move a substance against its electrochemical gradient. For example, co-transport of sodium glucose in the proximal tubule. So in this case, glucose moves against its gradient via secondary active transport. Here is an example of secondary active transport. In the renal proximal tubules, glucose is reabsorbed in the proximal tubules via secondary active transport. Here's the lumen. Here's the luminal membrane. Here is the basolateral membrane. Sodium-potassium ATPase is splitting ATP using the energy of hydrolyzing ATP to actively pump sodium out of the cell and pump potassium in the cell. By doing so, you are creating a low intracellular concentration of sodium. This creates an electrochemical gradient for sodium. Sodium moves inside the cell down its electrochemical gradient. As it does so, it uses the energy to pull in glucose. This is secondary active transport. This is the process of co-transport. This channel here is known as the SGLT2 channel. This channel uses secondary active transport. This is an extremely important channel in renal physiology. If you were to give a drug that inhibits the sodium-potassium ATPase, you would have an increase in your intracellular concentration of sodium. You would lose the electrochemical concentration for sodium. Sodium would cease to move down its electrochemical gradient. Glucose would cease to go inside the cell. You would stop reabsorbing glucose. You would have a decrease in your intracellular glucose concentration, and you would stop reabsorbing glucose. So this is how secondary active transport works. Now, in the reabsorption of glucose, as your intracellular glucose concentration increases, another channel that you have on the basolateral membrane is the GLUT2 channels. So over here in the basolateral membrane, you have the GLUT2 channels. As glucose moves inside the cell from the lumen, and you have an increase in your intracellular glucose concentration, glucose will be transported via the GLUT2 transporters, via facilitated diffusion out of the proximal tubule cell into the peritubular capillaries. And this is how glucose is reabsorbed in the proximal tubules. Another example of secondary active transport is the sodium proton countertransport. This is another transporter in the proximal tubules. This depends on the sodium-potassium ATPase, setting up an electrochemical gradient, and this is how protons are secreted in the proximal tubules. Now, for every proton that's secreted, a bicarbonate molecule is reabsorbed. Okay, this slide is very important. This slide looks at several very important equations that you are going to have to calculate in renal physiology. So let's take a look at this slide. This slide looks at how the nephron handles solutes and how you can calculate the excretion rate from the filtered load. Now, the filtered load is equal to GFR times plasma concentration. This is an equation that you must know and love in renal physiology. Write this formula down, know it, love it, understand it. Filtered load is equal to GFR times plasma concentration of a substance. What this means is how much of substance X is filtered right here at the glomeruli. To figure that out, you need to know the GFR times the plasma concentration of that substance. That's the filtered load. Here's another great equation you have to know. Excretion rate. Excretion rate is equal to urine concentration of a substance times urine flow rate. That's the equation for excretion rate. Excretion rate, once again, is how much, what amount, how many milligrams of a substance is excreted in the urine in a given minute. You have to know this equation. Urine flow rate. I want to spend a minute on urine flow rate. What is urine flow rate? Urine flow rate is the volume of urine that a patient produces in a given time unit. Urine flow rate is the volume of urine the patient produces in a given time unit. So you will give the patient a bucket or a urinal. They will take it home with them. For the next 24 hours, they will urinate in this bucket. 24 hours later, they will bring this bucket to you. They will hand it to you. And you will say, thank you very much for this wonderful gift. Thank you for this bucket of urine. You will measure this. This will have a volume of urine in it. Let's say the volume was 1 liter. That's the volume. The urine flow rate would be 1 liter per day. 1 liter, that's the volume per day. That's the time unit. That is the urine flow rate. Every time you say the word rate, you have to see a time unit. You can convert that to milliliters per minute. How many milliliters did the patient make in 1 minute? It's very important to understand what V means. Urine flow rate, the volume of urine that the patient makes in a 24-hour period, or the volume the patient makes in a minute. That's the urine flow rate. So, filter load excretion rate. Now, your filter up here in the glomeruli, your excretion rate is in the urine. Don't forget what happens. What happens in between filtration and excretion? Well, you might be reabsorbing, you might be secreting. So now you have to think about reabsorption and secretion. And then the net result is excretion. So in between filtration and in between excretion is reabsorption and secretion. And where does that happen? That happens along the tubule. So it's reabsorbed, or the substance is either reabsorbed or the substance is secreted, and you have to look at that. If it's reabsorbed, you're subtracting. If it's secreted, you're adding. The net result is the excretion rate. And this is mass balances. And these are the equations you will see in renal physiology. Okay, let's look at some quantifying renal processes. Let's say they give you a substance that has no net tubular modification. What does that mean? Well, here's a substance like inulin or mannitol. Inulin is a substance that is freely filtered at the glomeruli. Inulin is not secreted. Therefore, the secretion rate is 0. Inulin is not reabsorbed. Therefore, the reabsorption rate is 0. So therefore, for inulin, the filtered load is equal to the excretion rate, because the reabsorption rate and the secretion rate are both 0, 0, 0, 0. So therefore, for inulin, the filtered load is equal to the excretion rate. Now here's a classic question you will see on step 1. They will tell you, please calculate the filtered load for inulin. And you will say, Dr. Noto told me about this in the videos. I remember him saying this. He said, I need, for filtered load, I need the GFR, I need the plasma inulin concentration. And the question will give you the GFR, but the question will not give you the plasma inulin concentration. So you see the GFR, but you do not see the plasma inulin concentration. So you're going to say, Dr. Noto, he led me in the wrong direction. Why did I listen to him? But here's what the question will give you. They will give you the urine inulin concentration. Then they will give you the urine flow rate. Urine flow rate is the volume of urine that the patient made in 24 hours. Okay, so it could be 1 liter per day. Could be 1.5 liters per day. The urine's urinating a lot. Or it could be 1 milliliter per minute. It's the volume of urine the patient makes in a time unit. What you're not going to do is you're not going to take the urine inulin concentration and multiply it by the GFR, because that's going to give you the wrong answer. And guess what? That will be a wrong choice. What you are going to do, the correct thing for you to do, is you're going to calculate the excretion rate for that patient. The excretion rate for that patient is urine concentration of inulin times urine flow rate. That will give you the excretion rate of inulin. And for inulin, the excretion rate is equal to the filtered load. So if you take the urine concentration for inulin and multiply it by the urine flow rate, that will give you the excretion rate. And the excretion rate is equal to the filtered load for inulin. And that is how you will calculate the filtered load for inulin. That's a classic question you will see in renal physiology. Once again, be careful. Do not take the urine inulin concentration and multiply it by GFR. That is the incorrect answer, and you better believe that will be one of the answer choices. Okay, reabsorption. If the filtered load is greater than the excretion rate, how can you explain that? The substance was reabsorbed. If the filtered load is greater than the excretion rate, the substance was reabsorbed. Glucose, sodium, urea. Yes, I said urea. We'll get back to this later. Urea is reabsorbed. You have to know that for step 1. You better know that for step 1. Urea is reabsorbed. If a substance is completely reabsorbed, the excretion rate is 0. That's what happens to glucose. It is completely reabsorbed. Excretion rate is 0. So, for a substance that is reabsorbed, the excretion rate is equal to filtered load minus reabsorption rate. So here's what step 1 will do. They'll ask you to calculate the excretion rate. They'll ask you to calculate the filtered load, and you will. And let's just say the excretion rate comes out to, 100, but the filtered load comes out to 150. They will say, which of the following substances is this? This is a substance that is reabsorbed, because the filtered load is higher than the excretion rate. And that's a classic example. Or they may ask you to calculate the reabsorption rate from these numbers. So you'll get some calculations on the exam. Secretion. If the filtered load is less than the excretion rate, the explanation is the substance is secreted. If the excretion is higher than the filtered load, this is a substance that is secreted, PAH and creatinine. Creatinine is freely filtered and a small amount is secreted. So here the equation is excretion rate is equal to filtered load plus secretion rate. So here's what they'll do here. Again, they'll give you numbers. They'll give you GFR. They'll give you plasma concentration of a substance. You will calculate those numbers, and that will give you the filtered load. So it'll give you substance X, for example. Here's substance X. You're going to take the GFR. You're going to take the plasma concentration of substance X, and that will give you the filtered load. And let's just say that comes out to be 100. Then you're going to take the urine concentration of substance X and the urine flow rate, and you're going to calculate the excretion rate. And let's just say that comes out to be 150. Well, in that situation, you're going to see that the excretion rate is higher than the filtered load. So in that situation, again, the excretion rate, let's say, is 150, and the filtered load is 100. Well, the excretion rate is higher than the filtered load. And they will say, which of the following is substance X? The answer is substance X is something that is secreted. Substance X is either PAH or creatinine. And that's what they'll do with secretion. So to summarize net transport, filtered load minus excretion rate, equation for filtered load, GFR times plasma concentration of substance X. Excretion rate is urine concentration of substance X times urine flow rate. You're going to do calculations. If the net transport is 0, there's no net transport, that's inulin. If it's positive, substance is reabsorbed. Negative, substance is secreted. Okay, so let's do some practice questions just to give you an idea. These are some questions you might see. So calculate the reabsorption rate for glucose. GFR is 120 milliliters per minute. Here's your plasma glucose concentration. So what you're going to do here is your reabsorption rate is going to be equal to filtered load or filtration rate minus the excretion rate. So here's your urine flow rate, 2 milliliters per minute. Here's your urine glucose concentration, 10 milligrams per minute. So the answer is the reabsorption rate of glucose is going to be equal to the filtered load, which is GFR times plasma glucose concentration. So 120 times 3 is your filtered load. So that's your filtered load. Then you're going to take urine concentration of glucose times urine flow rate, and that's going to give you the excretion rate. And you subtract that, and you see that the reabsorption rate of glucose comes out to be 340 milligrams per minute. And that's the reabsorption rate of glucose. So this is a classic calculation that you will see in renal physiology. So be familiar with these types of calculations. So again, I said this in the very beginning of this lecture. This is the equation for mass balances. You must know these equations. So again, reabsorption rate of glucose will be equal to filtered load minus excretion rate. You calculate the filtered load using GFR times plasma glucose concentration. You calculate the excretion rate using urine concentration times urine flow rate. You subtract the two, and that's your reabsorption rate. Here comes out to 340. So that's a classic calculation you will see on renal physiology. So I know you guys are having a wonderful time thinking how amazing renal physiology is, thinking how there's nothing else you'd rather be doing right now than learning renal physiology. But it's about to get better, because now we have to talk about the concept of clearance. Clearance is a theoretical volume of plasma from which a substance is removed over a period of time. That's what the concept of clearance refers to. Basically, if a substance is filtered and then not fully reabsorbed, or if a substance is filtered and secreted and it appears in the urine, or if a substance is excreted in the urine, it is cleared from the plasma. Or if a substance is filtered and then completely reabsorbed, that substance is not excreted and the clearance is 0. Albumin, for example, is not filtered. Therefore, albumin is not cleared. Let's take a look at the kidney. Here's your kidney. Here is the renal artery. Renal artery has plasma that enters the kidney. In the kidneys, you have your processes that we spoke about. You have filtration, reabsorption, secretion, excretion. Albumin goes through none of those. Albumin is not even filtered. So the same amount of albumin that enters in the renal artery leaves in the renal vein. The clearance is 0. Glucose is filtered and then fully reabsorbed. So if 10 molecules of glucose enter the kidneys, 10 leave. Therefore, 0 molecules are cleared. So clearance, again, is the volume of plasma from which a substance is removed. That's what clearance means. So, for example, glucose has a very poor clearance. It is not cleared because it is not excreted. And that's the basic concept of clearance. So when you talk about clearance, what we're looking at is the plasma in the renal vein, because that's the plasma that has entered the kidneys and is now leaving the kidney. So we have to look at the plasma in the renal vein to see if the substance was actually cleared by the kidneys. Very important to realize that what you cannot look at is the excretion rate alone. You have to compare the excretion rate to the plasma in the renal vein. And that's what we're going to look at right now. Let's look at some example calculations of clearance values. Let's look at the plasma concentrations of molecules per liter. So here is 1 liter of plasma. 1 liter of plasma enters the kidneys, and that 1 liter of plasma, let's say, contains 4 molecules. And let's say the excretion rate is 4 molecules per minute. You're going to take those 4 molecules out of the plasma, and you're going to put those 4 molecules into the urine. Excretion rate is 4 molecules per minute. That's the excretion rate. We say that we cleared 1 liter of plasma. That's the volume of plasma that we cleared for that patient. That patient is filtering at 100%. The GFR is 100%. That's a normal GFR. Now, let's say a patient has a plasma concentration of 2 molecules per liter. Patient is still filtering at 100%. This time, the excretion rate is 2 molecules per minute. That patient still cleared 1 liter of plasma. Notice the patient on the top and the patient on the bottom, they both cleared 1 liter of plasma, but the patient on the top has an excretion rate of 4, and the patient on the bottom has an excretion rate of 2. Now, let's look at the patient in the middle. Let's say this patient is filtering at 50%. This patient has a GFR of 50%. This time, the plasma concentration is 4 molecules per liter, but you're only filtering at 50%. This time, you're going to take 2 molecules and place them in the urine. The excretion rate for this patient will be 2. What happens to the other 2 molecules? Well, they will stay in the plasma. So 2 molecules are excreted in the urine. Your excretion rate is 2. The other 2 remain in the plasma. So now, when we look in the renal vein, we will see 2 molecules left in the renal vein. We no longer cleared 1 liter of plasma. We now say that we cleared half a liter of plasma because 2 molecules have remained. Notice that the patient in the middle and the patient on the bottom have the same excretion rate, 2. They both have the same excretion rate, but the patient in the middle only cleared half a liter, whereas the patient on the bottom was still clearing 1 liter. So again, the excretion rate does not tell you clearance, and that's an important concept to understand. The excretion rate does not tell you the clearance. You cannot look at the excretion rate. You have to look at the plasma concentration in the renal vein, because the plasma concentration in the renal vein, that is what's important. That tells you clearance. That tells you the volume of plasma that was cleared. You see in the bottom, you cleared 1 liter. You're still filtering at a normal GFR. But in this patient, you only cleared half a liter. This patient has a decrease in clearance. This patient has a decrease in filtration, a decrease in GFR. Whereas this patient still has a normal clearance. Excretion rate is 2. Patient on the top has excretion rate of 4, but is still clearing 1 liter. So again, you cannot look at the excretion rate alone because you do not know the concentration of the plasma entering the kidneys in the renal artery. So again, you have to look at the plasma concentration in the renal vein to determine the clearance. And that's how you calculate the clearance. Therefore, the 2 factors that determine clearance are the plasma concentration of the substance in the renal vein as well as the excretion rate. So the equation for clearance is the following. And you have to know this equation. You will be asked to calculate it on step 1. Excretion rate over plasma concentration of substance X. Excretion rate we looked at. Excretion rate is the urine concentration of substance X times the urine flow rate over the plasma concentration of substance X. This is the equation for clearance. Be familiar with it. You will be asked to calculate this on the exam. So let's look at some practice calculations. Here's your urine flow rate, 2 milliliters per minute. Here's your urine concentration. Here's your plasma concentration. You take the urine flow rate times the urine concentration, which would be 4, and put that over the plasma concentration. The answer comes out for substance X comes out to be 2 milliliters per minute. Substance Y. Notice the urine concentration is 0. That means 0 was excreted. That means 0 was cleared. So clearance of substance Y is 0. If it's not excreted, it's not cleared. Substance X. Urine flow rate times urine concentration. 2 times 0.5 would be 1. Put that over the plasma concentration, which would be 1. And the clearance here for substance Z would be 1 milliliter per minute. And that's how you calculate clearance. So be familiar. You may be questioned on this.